Hello again. In this video, we're going to talk about existence of solutions to matrix equations. The matrix equation AX equals B has a solution if and only if B is a linear combination of the columns of A. i.e., that's the same thing as asking, is B in the span of the columns of A? Or, i.e., is AX equal B consistent? A harder existence question to ask is whether AX equals B is consistent for all possible B. And that's what we're going to do in example 3. So example 3 says, let A be this 3 by 3 matrix and B be an element in R3, B1, B2, B3. Is the equation AX equal B consistent for all possible B1, B2, B3? So we saw from the last video, AX equals B. Here's A, which in this case is a coefficient matrix, times the X. X needs to be in R3, because this is a 3 by 3, so we have to multiply this by a 3 by 1 to get B, which is a 3 by 1. And if you multiply this out, we get a linear combination of the columns of A, where x1, x2, and x3 are the weights. And we saw from the last section, this question, finding all possible values of B1 and B2, B3. And this equation, this vector equation, finds the span of the columns of A. So let's go ahead and do that. What is the span of the columns of A? We also saw from the last video that this also represents our system of equations. So we can also write this as the augmented matrix. And we're asking the same question. Is the system consistent? So we're going to find all possible B1s and B2s and B3s. And we're going to also, at the same time, ask what is the span of those columns? So I'm going to put this in echelon form. Once again, leaving the first column alone, I'm going to get a 0 where the -4 and the -3 are. So I'm going to multiply the first row by 4, add it to the second. Doing the same thing for the third row, I'm going to multiply this by 3, the first row by 3, and add it to the third. Now for simplicity, I'm going to interchange row 2 and row 3. And now I'm going to use this one as my pivot. So I'm going to multiply the second row by -2 and add it to the third, where the last column is going to be in terms of B1, B2, B3. So that's going to be 0, leaving the first 2 rows alone, 0. Oh, this will be, 0. Uh-oh. This one will be a 0, 2. And then we're going to get -2 times 3B1 plus B3, and then added to 4B1 plus B2. Since we have a row of zeros here, the system is only consistent when this last entry right here is 0. The entry that is in the last row and last column. Simplifying this a little bit by getting rid of the parentheses and combining like terms, and then I decided to multiply through by a negative, you get 2B1 minus B2 plus 2B3 equals 0. So this description describes all the B for which our original AX equals B is consistent. It also is the span of the columns of A. And here's a picture here of the span of A1, A2, and A3, where A1 is the first column of our matrix, A2 is the second, and A3 is the last. So the columns of A span a plane through 0. So there it is the plane through 0. And it failed to be consistent for all B because we had a row of zeros here. We only had 2 pivots. We did not have 3 pivots. So let's look at an example where it would span all B. So here's a simple example. Is AX equal B consistent for all B, where A is this 2 by 2 matrix? A simpler question. You can visualize it maybe a little better. And again, asking this question is going to be equivalent to asking the question, what is the span of the columns of A? So this time, I'm just going to start with the augmented matrix, but make sure you know the logic of the first one of why that is. It shows it up here, but I'm just going to start right here. So getting a 0 in the first row of the second column, I'm going to just multiply the first row by -1 and add it to the second row, leaving my first row alone. So I would get 0, 2, and this would be a negative B1 plus B2. We could stop there on this one because we have 2 pivots. There is nothing that B1 and B2 cannot be. B1, B2 can be any number. So the answer to this one is yes. AX equals B is consistent for all B in R2. And what is the span of those column vectors of A? It's going to be R2, since B was in R2. If, for instance, on this question in example 3 was yes, if there happened to be a pivot for this value right here, then it would have been the span of the column vectors of A would have been all of R3. But because it wasn't, it was a plane in R3. Which brings us to the next theorem. It says here, let A be an n by n matrix, then the following statements are all logically equivalent. That is, for a particular A, either they are all true, all the statements are true, or they are all false. So the first one, for each B in Rm, B needs to be in Rm because we have an m by n matrix, and the X needs to be in n, and the result is m by 1. So B is in Rm, and it says for each. The equation AX equals B has a solution, which is the same as above here in this last example, because it says for each. So that means B has a solution for all of B in Rm, which we saw above here in example 1. That means that the span of the columns is all of Rm. In this case, it was all of R2, but the columns of A span all of Rm. And again, it's an Rm because it spans all of B, and B is an Rm. And we know part D is true, that A has a pivot position in every row, because that's how we find when it is sometimes not consistent, is when we have a 0 here. We do not have a pivot in this last row. We saw that. In this example, in the one before, we saw it didn't have a pivot position and how it didn't span all of Rm, or it didn't have a solution for every B in Rm. And then part B, I know I skipped that. That is just the definition of spanning. For each B in Rm, if you go back and look at the spanning, is a linear combination of the columns of A. And we saw this because we saw before in general that a set of vectors in Rm generates the whole Rm if and only if every vector in Rm is a linear combination of those vectors. i.e., saying it again, the span of a set of vectors equals Rm for each ai in Rm, there's n of them here, if every vector in Rm, that's our B, is a linear combination of a1 through an. So you can see why B is correct there. So that's the logic why each of these are true. If you want to actually see the proof, it is in the book at the end of this section. This is one of the most useful theorems in this chapter because of the definition of AX and what it means for a set of vectors to span Rm. Which brings us to the last theorem of this video on the properties of the product AX. The facts of the next theorem are important and will be used throughout the text, and the proof really just relies on the definition of AX and the algebraic properties of Rn. So here's the theorem. It just says that if you have a matrix, an n by n matrix, that is, and U and V are an Rn, they need to be an Rn again to make the multiplication defined, and C is a scalar, then you have these two properties. A times U plus V, the distributive property of the matrix A with the vectors U and V, is AU plus AV, and the scalar multiplication here, A times CU, you can bring that C out, that constant out. Here is the proof. You can find this proof in the book. For simplicity, the book took n equals 3, though you could do this for the generic case and it would be very similar. But taking n equals 3, that we just have 3 vectors here for A, and U and V are in R3. So what we're going to look at is matrix A on the left side here, times U plus V, vectors U plus V. So we have A, and then we're going to call this U1, V1 for the first entry of U plus V, U2, V2, and U3 plus V3. You multiply this out, you get this linear combination. You use your algebra, and you can see that's clearly AU plus AV. Then they did the similar thing with B. You can clearly see when you put a CU1 here, that when you multiply it out, you're going to get CAU1. So you could check this out in the book. That is it for this section.